Okay, let us move on to the next question. Next question is question 3. Again, the same type of question that we saw. It's about setting up the Lagrange multipliers and then applying the techniques. Just setting this up, and I'm not going to go over the details, just to set up for you. So for question 3, what do we have? We have the space prop and the shape of ellipsoid. You have a space prop, and the shape is an ellipsoid with the formula for x squared plus y squared plus 4z squared equals to, well, 16. So it means that the constraint is given to us. This is your g function. And then it enters the Earth's atmosphere and its surface begins to heat. Of course, after 1 hour, the temperature on the surface prop is T of x, y, and z equals to, well, 8x squared plus 4yz, and then minus 16z plus 600. Question says, find the hottest point on the space. Find the hottest points on the space. Very well. So let's see what do we have here. If you just write z in terms of x and y and substitute that here, again, you end up with a function in 2 variables. Then what you can do, you can go back to Hessian matrix and use the determinant to find the discriminant and use that method as well. So one method is to write 4z squared equals to 16 minus 4x squared minus y squared, and your z is equal to plus minus square root of 16 minus 4x squared minus y squared divided by 4. Substitute into function z, in this case function t of x and y and z, to get t of x and y, then apply the discriminant method. This is one method if you're interested in using this method, seeing how it works. Of course, why not? We learned different techniques in calculus. Let us use some different techniques. Or another method is the Lagrange multipliers. So they need to take the derivative of the function that we're trying to maximize, minimize. Remember that here we're looking for the hottest points. So gradient of t equals to lambda, the gradient of the space prop shape. Let us call it function g of x, y, and z. Well, the gradient of t with respect to x, you get 16x, and comma, gradient with respect to y, 4z, and the gradient with respect to z, plus 4y minus 16 equals to lambda, then the gradient of function g with respect to x, 8x, 2y, and 8z. And the rest, as you know, setting the first components equal to each other, setting the second components equal to each other, setting the third components equal to each other. Then try to figure out what is x in terms of the rest of them, and you can actually work with lambda as well. Here, if you plug in lambda as 4z divided by 2y, then you can plug that guy in here and try to see if you can find a relation between y and z. So use algebra to find the values for x, y, and z. So if you solve for your lambda in the first one, in the first equation, if you solve for your lambda, just a general idea here, your lambda is going to be 2. Well, if lambda is going to be 2, then, well, what else we have? We can use these two equations. Since these two equations, they have two variables, we can use intermediate algebra to solve this. We get 4z equals to 4y, and z is equal to y. And then into the second equation, you get 4y minus 16 equals to 16z. And since z and y are equal to each other, it's going to be 16y. Well, here, if you solve this, what we get 12y is equal to negative 16, or y is equal to negative 3 divided by 4. Y is negative 3 divided by 4. Y and z are equal to each other, so you get z also negative 3 over 4. Then you can use your g to find your x. Use g to find x. In this case, your x is going to be plus minus 4/3. So we're going to get two values for our x. So by solving this, the first equation, solving for lambda, we get 2 points. 4/3, negative 3. Let me see if it's correct. Negative 3 divided by 4 and negative 3 divided by 4. And the second point, negative 4/3, negative 3 divided by 4, negative 3 divided by 4. Now you have to plug these two into the temperature to find the temperature at each. So the temperature is approximately, let's see, almost 643 degrees, almost 643 degrees. Well, the other one is from the first equation, if lambda is not equal to 2, the only option that we have is x equal to 0. So if lambda is not 2, then x must be 0. So x is 0, and then your lambda from the second equation can be written as, well, 4z divided by 2y. So lambda is equal to 2z over y, and then substitute that in the third equation, and you get 4y minus 16 equals to 8, 2z over y times z. Then continue solving for, solve for y and z. Now the points that you should get are 0, -2 square root of 3. Now let me see. And 0, -2, negative square root of 3. 0, -2, and negative square root of 3. So if you calculate the temperature at these points, you approximately get, let's see, 642, almost 642. So the temperature is approximately 642 degrees, which are less than the temperature at these 2 points. So your space prop is going to take its maximum temperature at these 2 points, plus minus 4/3, -3/4, and -3/4. Very well. So don't forget to flip these. 16 divided by 12 is -4/3. And next question, question 4. Okay, so say calculate the double integral. Let's see. So this is one of the examples that's showing that sometimes they have to switch the order because it's impossible to calculate the integral itself. So for question 4 says, well, calculate the double, let me find the double integral. Calculate the double integral. What is the double integral of sine x divided by x dA, and the region R is given to us as a triangle in xy plane and bounded by x-axis, and line y equals to x, and another line, which is your vertical line, x equals to 1. Well, what is our first step? Our very first step is to graph this region. To graph this region, what do we have? We have x-axis, which is just right here, y equals to x, which is this line here, and then x equals to 1, which is this vertical line here. So this is the region that you're dealing with. This is your region. Well, okay, you might say that, hey, my x is bounded obviously between 0 and 1. And my y takes its smallest value, and then it takes the maximum value at this line. So my y is bounded between 0 and x. So if I set it this way, I'm going to convert this double integral sine x over x, then dy dx. My y is bounded between 0 and x, my x is bounded between 0 and 1, and it helps me to calculate this integral easy. Why is that? Here, this guy doesn't have any y in it. It means that it's just a number, a coefficient. You get the integral 0 to 1 sine x divided by x, and the integral of dy as y ranges between 0 to x is going to be x dx. Of course, we can cancel out x and x. We're left with a simple integral 0 to 1 sine x dx, which is negative cosine x, 0 to 1, negative cosine y, 1 minus cosine 0. This is just 1. So you get 1 minus cosine 1. You can use a calculator to approximate this number. For approximation. approximation. Just note that if you write it the other way, the calculation is going to be very hard. If we use the boundary, y is bounded between 0 and 1, and x is bounded between the line y and the vertical line 1, then the calculation is difficult. It's not impossible, but it's going to be difficult. You have to use integration by parts and other techniques to calculate this integral. Very well, let us move on to the next question. Question 5. Question 5 says, find the double integral of y minus, this is your ceiling that you have, 2x squared dA over this region. What is the given region to us? Given region is, okay, R, absolute value of x, absolute value of y equals to 1. Okay, so remember that we're interested in visualizing the region. Take a look at this. How do we analyze this region based on the definition of absolute value? Absolute value of x can be plus minus x. Absolute value of y can be plus minus 1. So what do we get? We get x plus y equals to 1. Let's take a look at this. What is this line? Y equals to 1 minus x. Well, this line is going to be just right here. Y equals to 1 minus x. Okay, absolute value of x can be negative x. Negative x plus y equals to 1, or y is 1 plus x. 1 plus x. Very good. So here we're going to have an increasing line, and this is 1, negative 1. So this is the graph of y equals to 1 plus x. Now we have to analyze absolute value of y. So x can be positive, y can be negative. What is this line? Y equals to x minus 1. Well, so if I plug in, for example, 0, I get negative 1. If I plug in 1, I get 0. So this is this line segment here. This is y equals to x minus 1. Now, for y to be negative and x to be negative, y is negative x minus 1, which is this piece here. Y is negative x minus 1. What we're going to do, we're going to take this guy and divide it by 2 sections, 2 portions. One portion here and the other portion here. Why is that? Because of the ceiling that I have. So this is my next portion. We are calculating 2 double integrals. Calculating 2 double integrals because of the behavior of the ceiling and of course because of the base that we have. So the first one is going to be having x bounded between 0 and 1. X is bounded between 0 and 1. Then my y is bounded between x minus 1 and 1 minus x. X minus 1 and 1 minus x. And the ceiling is y minus 2x squared dy dx. And the second double integral, my x is between -1 to 0. And my y is bounded between -x minus 1 to 1 plus x. And this is my ceiling that I have, y minus 2x squared dy dx. After calculating these two, you're going to add these together.
Okay.